This is chapter 7 continued. We are discussing the systems of particles, and this is applied physics for undergraduate students. And I am Dr. Nasir Mirza, and we will be talking about the systems of particles in the today's talk. It is the second part of the systems of particles. We have already gone through this, that Moon and Earth form a two-body system, and the center of the mass of the Earth-Moon system follows nearly a circular orbit about the Sun. And you can see here the dark red-colored path is that circular path, which is the center of mass path. While the Earth and the Moon are rotating about their common center of mass, just like a baton, the effect is really causing a slight wobble in the orbit of the Earth. And in this figure, it is really exaggerated, this wobbling of the Earth about the orbit. And you can see the Moon connected to the Earth, and it's the center of mass as a black dot, and the Moon is showing the rotation. The center of mass of the Earth-Moon system actually lies within the Earth. So the Earth is always overlapping the orbit and orbital path, and we can assume that the center of the mass of this type of a system is really enough to describe the complete system. So this example is to tell you that Moon and Earth's motion is really the center of the mass of the Moon-Earth system, and it follows a circular path. We have already gone through this example in which there were three particles. They were attached, and they were making a rigid body, and the distances between them were A, and A. And we were asked to find out the center of the mass. So we have used the graph to read the values, and initially we had substituted our coordinate system so that the 0, 0 of the coordinate system was lying on one of the masses. And it has really reduced the effort to find out the center of mass. Here, particle 1, 2, and 3 with the mass 1.2, 2.5, and 3.4 kg are shown, and their respective x coordinates 0 and 140 and 70 centimeters are shown, and y coordinate as 0, 0, and 120 are also shown. Then the coordinate of the center of mass can be calculated with the help of this weighted values. The x for the center of mass is equal to 1 divided by the total mass, sum over all particles, mi(xi), and it is actually equal to m1x1 plus m2x2 plus m3x3, and divided by the total mass. Once we substitute the values, we find out that its overall result is 83 for the center of mass. Similarly, the y value for the center of mass is 1 over the total mass multiplied by the sum of mi yi, which is the m1 y1 plus m2 y2 plus m3 y3, and once we substitute the values, we can find out the y coordinates. That is how we find out the position vector r for the center of mass, and we point out this r from the origin, and you can see it is shown here as a vector and a red colored position for the center of mass. The value for x is 83 and value for y is 58. The center of mass for the solids or the solid objects that are really containing many particles or many atoms, then we can best treat them as continuous distribution of mass. We can also assume that the particles are differential masses or the differential mass elements given by small elemental mass dm. Then sum becomes integral, and the coordinates of the center of mass are then defined as following. The center of mass is given as 1 divided by m for the x coordinate, integral of x multiplied by dm. Similarly, integral for y dm multiplied by 1 over m is the y coordinate, and z dm integral multiplied by 1 over m is the z coordinate. Here m is the total mass of the object. We know if the object has a uniform density, then this density is given as dm over dv. We can also say that this is mass per unit volume. So we can substitute for dm the rho, the uniform density multiplied by dv. We can also substitute for the mass as the rho multiplied by v. Then we have this new equations. Set is looking like this. X for the center of mass is given as 1 over volume integral of x dv. Y for center of mass 1 over v y dv integral, and 1 over v integral of z dv as the z coordinates for the center of mass. So center of mass of the object can be computed, and it need not lie within the object. It can be outside, and the method to calculate is this. So instead of calculating with the help of the mass distribution, we can have the volume distribution to find out the integral. This example is showing a uniform metal plate P of a radius 2r. This is the radius 2r, which is a disk of radius r, as a white colored, and it has been stamped out or removed from the larger disk in an assembly line. Using the XY coordinate systems shown, we have to locate the center of mass, the COMP, for the remaining disk, which is shown here as a green colored dot. So let us identify a few things for this problem. First of all, there is a plate P, and the center of mass for the plate P, overall, this is the plate P. The green colored thing is a plate P, which has a center of mass given as COM with subscript P. And the location is given as XP. The mass of the disk is MP. Similarly, there is a disk S, which is stamped out disk, and this disk has a radius r, and its center of mass is COM subscript S, as shown here with the yellow color. And the radius is minus r because it is on the x-axis, as you can see, at a distance r away from the origin towards the minus x direction. The whole mass of this thing is ms. Similarly, we have a plate C, the composite plate, which is containing all things. That is the plate for which we are figuring out or trying to figure out, and also the plate which has been stamped out. The total plate is C, the composite, and X for the composite is at the origin 0 location, and the mass is given as ms plus the mass of the plate. So now coming back to the center of mass problem, the mass of the uniform object is concentrated in a particle at its object's center of mass. So the x coordinate for the s plus p is given as weighted for the stamped and for the plate. And so it is ms x s plus mp xp divided by the total mass. However, xp is given as the ratio, we can see that it is the ratio minus xs multiplied by ms divided by mp. And this is due to the fact that the composite has the answer equal to 0. Because xp, the composite coordinate, as we have seen, that the composite has the x equal to 0. So this s plus p coordinate is 0. Therefore, this mass is not 0. Then weighted values sum is equal to 0. And from that, we come to know xp equal to this minus times. Now we know the areas ratio, the area of the stamped divided by the plate area, the ratio is the area of the stamped divided by the area of the total minus the area of the stamp. And we can calculate pi r square, pi 2r square minus pi r square, and the overall answer is 1/3. Therefore, ms and divided by mp ratio is 1/3. And once we substitute here, we get that xp is equal to 1/3 times the x value for the center of mass of the stamped, and it is equal to minus r. Therefore, this overall answer is 1/3 times r. And that's how we have calculated the center of mass of the composite equal to 1/3 times r. Moving further in this, we must now focus on the conservation of momentum in a system of particles. If there are several particles, and suppose we have a system of particles that are based on n particle system, then particles having mass mn, n is equal to 1, 2, 3, 4, up till n, so they are moving with certain velocities. So velocities are v1, v2, v3, vn. Therefore, the momentum is for nth particle given as mn into vn. So we can write the total momentum of the system as sum of the momentum vectors p1 vector plus p2 vector plus p3 vector plus p4 vector and so on up till pn vector. So this is the total momentum. And it can be described as the product of the mass and velocity m1 v1 vector plus m2 v2 vector plus m3 v3 vector, so on, mn vn vectors. Now this whole thing is equal to the m, the total mass, multiplied by the v, velocity of the center of mass. And from this, we conclude that the linear momentum of the system of particles is basically equal to the product of the total mass of the system multiplied by the velocity of the center of the mass. You can see from this equation m1 v1 plus m2 v2 plus m3 v3, this is looking like we have already seen for the center of mass. So if I divide this whole thing with the mass m, the total mass, and multiply this with the total mass, then m m can be agreeably figured out as a weighted thing for the momentum. And this is the weighted momentum for the center of mass. So we conclude that the velocity of the center of mass multiplied by the total mass is the momentum. So it looks like that n particle system, when it is moving with different velocities and all have the different values of the masses, then their total momentum is given by the total mass multiplied by the velocity of the center of mass. So it looks like that whole mass is concentrated at the center of mass, and the total system is moving as if it is the center of mass which is moving. Now assume that we have a constant mass m, then derivative of the momentum is dp over dt, and it is equal to mass times dv over dt, and v is here v of the center of mass. If this is the case, then mass times acceleration is the answer for this rate of change. In fact, this rate of change of momentum is, according to Newton's second law, equal to the sum of the external forces. So this is the sum of the external forces or the net force. So rate of change of momentum or the net force is equal to mass times the acceleration of the center of mass. So total momentum of the system of the particle is the product of the mass of the system multiplied by the velocity of the center of the mass, and the rate of change of this momentum is basically the external force, and it is given by the acceleration of the center of mass. Let us do one example which is based on an exploding projectile. Previously, we have considered a ball or a mass or a point-like object which has been thrown into the air with the initial velocity, and it goes like a projectile, it goes like a parabola. Only the gravitational force keeps on acting on that object towards the center of the earth, and under that influence of that force, ignoring all the friction and the air resistance, we see a projectile motion. Here, a case is slightly different. A projectile is fired into the air, and then it suddenly explodes into several fragments. So a projectile is thrown and it goes in air, and here it explodes. It explodes into several fragments. Now, what we can say about the motion of the center of mass of the system made up of all these fragments after the explosion? So this is the question. To answer this question, we first of all neglect the resistance. The only external force on the projectile is the gravitational force, and the gravity is in the downward direction. And the component of velocity is horizontal and a vertical. And if the projectile never exploded, it will keep on tracing a parabola. So we know very well, according to the classical mechanics, a projectile, if it does not explode, it will continue to move along a parabolic path. And it's as indicated by the dashed line here in this figure, it will trace that type of a equation looking like a parabola, where y is proportional to x square. Because the force is caused by the explosion, and the explosion is an internal explosion, it is caused by the things in it. They do not affect the motion of the center of mass of the system. The fragments that are scattering have a certain center of mass. And after the explosion, the center of mass of the fragment will keep on following the same parabolic path that was being traced by the projectile, as if there was no explosion. So this problem gets simplified. If there is no external force acting on the ball or this projectile, then internal force causing this explosion will keep the center of mass moving in the direction that is similar to the original initial direction. So the fragments may be getting scattered everywhere. However, the center of mass will follow the motion as dictated by the original parabol. This is due to the fact that the explosion was caused by the internal forces. If there were external forces, the projectile would have accelerated with it and then would have caused a different kind of a parabola. But again, the center of mass would have followed that acceleration. Let us do this example of exploding rocket and find out what are the ways to rightly explain the velocities or the components of different fragments if they are there. For example, a rocket is fired vertically upward. At an instant, it reaches an altitude of 1000 meters and it gains a speed of 300 meters per second. It explodes into three fragments having equal masses. Although this is a rare event, but it happens. One fragment continues to move upward with a speed of 450 meters per second following the explosion. The second fragment has a speed of 240 meters per second and it keeps on moving east right after the explosion. And these are the observations, experimental observations. Then question is asked, what is the velocity of the third fragment right after the explosion? So many things have been given and we are asked to use those things or informations to our problem's solution. So let us define few things and then try to solve the problem. The mass of the rocket is m, then mass of the each fragment is m divided by 3. We are not given with the mass. The momentum before and after the explosion can be considered as Pi and Pf, P initial and P final. We are defining only this. We also say that in the positive direction of x-axis, the unit vector is I, and along the positive direction of y, the unit vector is j. If there was a third dimension, then unit vector k would have done that direction. Now we write down the momentum before collision or before explosion. The momentum before explosion is defined as Pi, the initial momentum, equal to mass times velocity which is initial velocity. Now we know that the initial velocity, when it reaches the altitude of 1000 meters, a speed of 300 meters per second is there. So mass times 300 meters per second speed is there, but it is vertically upward, so it is a j unit vector which has been used. So we can see that the j unit vector is telling that this is vertically upward speed. Then we have the final momentum, which is given by Pf, and it is for the three fragments, and three fragments have mass divided by 3, the total mass divided by 3, because it is said in the question, it explodes into 3 fragments having equal mass. So m by 3 is the mass, m by 3 is the mass. The first fragment is moving upward with the speed 450 meters per second. So this is the component m divided by 3 multiplied by 450 times j unit vector meters per second. Then there is other second fragment which has a speed of 240 meters per second, 240 meters per second. It is moving east. So on this paper, the east is the positive x direction. So it is moving towards I unit vector. 240 meters per second times I unit vector is the second fragment. Then we come to the third fragment, and the third fragment is moving with some velocity v. We don't know that velocity, and the question is, what will be the velocity of this third fragment? So we substitute here m divided by 3 times this unknown velocity v. Because the conservation of momentum says that the initial momentum must be equal to the final momentum, then we give this type of a balance. Final momentum is m divided by 3 times Vf plus m divided by 3 multiplied by 240 times I unit vector plus m divided by 3 450 times j unit. The whole thing is equal to mass times 300 times j, which is the initial moment. If we simplify, then we find out that the velocity vector, the final velocity for the third fragment, comes to be minus 240 times I unit vector plus 450 times j unit vector in meters per second. So, very simply, if rocket explodes into many pieces, for each piece, if we know the direction and we know the speed, then we know the momentum, then we can figure out unknown quantities. From the law of conservation of momentum, this can always be done. Coming to conclusion for this chapter, we see that the problem-solving strategies are always based on conservation of momentum. So first we identify the relevant concept, and we confirm that the vector sum of the external forces acting on the system of particles is 0. If it is not 0, we will not say that there is a conservation. Then we set up the problem using the following steps. We will treat each body as a particle. We will draw before and after the collision or the action sketches. We will include velocity vectors. We will also assign algebraic symbols to each magnitude and angle and the component. We will use letters to label each particle, and we will say subscript 1, 2 for before and after the quantities. We will also include any value uh, such as the magnitude, angle, or the components in this. We will define the coordinate system such that it will provide ease. We will show it in the sketches. We must define the positive direction for each axis very clearly, that this is the positive x direction or this is the positive y direction. Then we will identify the target particles or the target variables for which the answers are desired. Then we will solve. We will start the solution. To solve the problem, we first write an equation in the symbols that are used, saying total initial and total final x component for the momentum of each particle, and we will write corresponding equations for the y components or if there are z components. We will show the positive and the negative values. We will be very careful to the signs so that the velocity components are not really mixed, and we should not be creating errors only due to the directions. In some of the problems, energy considerations give additional equations, additional information that are related to the velocities. Then we will solve these equations to find out the target variables or their properties. At the end of this exercise, we must evaluate our answers. Our answers should make few important contributions. First is that the dimensions and the units must remain consistent. We must double check that the units and the dimensions are same. Also, our answers should make physical senses. They should be physically realizable quantities. They should not be hypothetical. If the target variables are, for example, some part of the problem's momentum or some component of the body where the momentum is desired, then we will check the direction of the momentum, and it should be very reasonable. Otherwise, our problem has issue, and we need to check. If there are issues, then we need to check. So evaluating solution, reaching at the solution, and then figuring out the proper answer to the problem is very much needed in all these exercises. One important contribution in the center of mass systems is that the center of the mass for many particle systems act like a single entity where the whole mass is concentrated. Its displacement, its velocity, its acceleration is actually representing the whole body. we end our discussion on the many particle systems and the associated center of mass for the systems of particles. Our next lecture will be the rotational kinematics and the details associated with the rotational kinematic equations. Until then, we stop here and end our discussion. Thank you so much.